Good evening, very warm welcome to the September meeting of Nottingham Astronomical Society. Tonight's lecture is by Dr. Chris Arridge, and his talk this evening is on the Plumes of Enceladus. Our online meetings programme for the rest of 2020 is now being confirmed, and you can see full details on our website. A meeting in a month's time is by Dr. Steve Barrett, and he'll be talking about the Hubble Space Telescope. And our meeting in a fortnight's time at Plumtree is going to be on planetary imaging. So our speaker this evening is Dr. Chris Arridge. He is a reader at the University of Lancaster in the Department of Physics. Chris's academic research is focused on the study of magnetised plasmas in the large solar system bodies and how they interact with our surroundings. Most of his work focuses on the giant planets of Jupiter and Saturn, with data analysis from space probes such as the Cassini mission to Saturn, on which Chris was a member of the magnetometer and the plasma spectrometer instrument teams. Chris is also co-investigator on JMAG and the PEP teams on the forthcoming Jupiter Icy Moon Explorer probe. So a very warm welcome this evening to Chris, and I'll hand you over to him for his talk on the Plumes of Enceladus.
Okay, thanks for joining me on this recording where we're going to be talking about the Plumes of Enceladus. And just so that we're all on the same page from the outset, when I'm talking about the Plumes of Enceladus, I'm talking about these jets that are coming off the limb, off the South Pole limb of Enceladus in this image in the top left-hand side of the slide here. So they are jets of gas and dust and icy material, and also more exotic and complicated molecules that emanate from the South Pole of Saturn's tiny moon Enceladus. And in the center here, we're seeing a really fantastic zoom in from the camera suite on the Cassini spacecraft, looking at some of these fractures that are on the South Pole of Enceladus, where these jets originate from. And so the scale is really fabulous on this image here. We're down to about 35 meters per pixel on this image from the South Pole. So that's what we're going to be talking about here. And so obviously we are in the outer solar system. We're in the distant regions of the solar system. So let's just sort of try and orientate ourselves a little bit of exactly what we're looking at, and let's take a look at some of the other objects that have sort of educated us and led us to explore these fascinating phenomena at the Saturnian system. So we are firmly in the realm here of the giant planets, the outer planets of our solar system, and these giant bodies are almost like miniature solar systems in their own right. We're looking at very large bodies with disk-like distributions of material around them, so rings, particularly obviously in the case of Saturn, and then a large number of moons trapped and in orbit around these bodies. So if we want to look at some of the architecture that we have here, this is a sort of a composite sketch showing some of the natural satellites in the solar system. So we're looking here, if I bring up my pointer again. So we're looking here at things that are all to scale. So we've got Earth in scale with the Moon, in scale with Mars, and in scale with the 4 Galilean satellites at Jupiter, and the main satellites at Saturn. And so we can see something of a disparity already. You know, we have these 4 rather large satellites, quite different satellites here at Jupiter, from Io through to Europa, Ganymede, and to Callisto. And then when we compare that with what we have at Saturn here, we've got a collection of smaller icy bodies in the inner regions out to Rhea, around about 9 or 10 times the distance, the equatorial radius of Saturn out in the system. And then the really dominant star of the show for some is this moon Triton, the second largest natural satellite in the solar system. And second, actually, to Ganymede. So Ganymede is this largest largest natural satellite in the solar system, natural satellite of Jupiter, larger even than planet Mercury. And in fact, you can see, comparing Ganymede and perhaps Titan with Mars, you know, these are not too far behind some of the larger planets that we might think of as being real titans, if you like, in our solar system. So we've got some really quite significant icy bodies here in the outer solar system, some large bodies which as we're going to find out, have got some really interesting physics and chemistry and geology going on underneath those surfaces. If we just focus in on the Saturn system for a moment, we've got this sort of sketch, like I said on the previous slide, of this being almost like a little solar system in miniature. You know, so we have our central body here with Saturn, just looking at the sketch at the bottom now with the main rings that you can see here. And actually the rings do go out further, as we're going to see right towards the end of the talk. And actually this ring called the E ring here, which only really shows up very strongly when you're on the other side of Saturn to the Sun. Enceladus, this tiny meteor, is embedded in that E ring at Saturn, and that location of Enceladus and the E ring, being located in the brightest part of the E ring, was one of the sort of smoking guns from the Voyager mission that told us, hey, there's something interesting going on here with Enceladus. It's not everything that meets the eye with Enceladus. So there's a very rich planetary system here with these rings, natural satellites, obviously the planet itself, and all of these different elements interacting with each other. So what I want to do is just dig a little bit more into some of these natural satellites, into some of these distant worlds. And our sort of perspectives on these distant worlds have changed quite a lot from going right back to the Voyager mission, when we first started to get images and measurements from the outer solar system beyond the asteroid belt. You know, so for example, in the Voyager images, we started to see active volcanism on Io for the first time. Active volcanism off Earth, away from Earth. You know, of course, we'd seen evidence of extinct volcanism on Mars, but this was seeing Io was the first time we actually saw that on another planetary body. So let's start off with Io, since I've already started there. So these are real color images of Io, and the different colorations that you're seeing is due to the sulfur compounds that reside on the surface. So Io is widely thought to be the most volcanically active body in the solar system. It's quite a small and tiny world, really, but a very, very active one for its size. You can see these blemishes all over the surface. Some of these have like sort of like curved features, linear features, splotches, almost look like spots in some ways. And these are lakes of lava. These are sites of active volcanism on the surface of Io. And the insert image here, this is an image from Galileo. And here we're seeing just the limb here, and you can see this feature that's been colored blue here. And this is an actual active volcanic eruption off the limb of Io. And we've seen this in subsequent images. We've seen this in a set of quite famous images from the New Horizons spacecraft. As it flew past Jupiter on its way to Pluto, it saw an active volcanic eruption with this plume that was extending hundreds of kilometers into space off the limb of Io. And when the infrared cameras on New Horizons looked at Io, it could see these spotches and blotches of heat on the night side of Io. And of course, these are all these sites of volcanic activity, showing that heat radiating out into space. So a very, very interesting world. And this extreme volcanic activity is powered by a tidal interaction. So just the same physics that gives us daily ocean tides on the Earth. The same thing happens at Io and some of the other Galilean satellites, and that's caused by a gravitational interaction between Io and the other satellites in the system. So as Io goes around Jupiter and the other satellites go around as well, periodically Io gets its shape squashed into an oval in one direction, then relaxes to be changed into an oval in the other direction, giving you this sort of almost like it's almost like squeezing a ball periodically. And that squeezing releases energy, deposits energy, tidal energy, into the solid crust of Io, and that energy goes into heating it up and driving all this volcanic activity. So this is Io. We're here about 6 Jovian radii out from the center of Jupiter. Next Galilean satellite out, we're going to skip that one, and we're going to go to the third one. And the third one is Ganymede. And this is, as I said, the largest natural satellite in the solar system. And it also has the honor of being the only satellite that we know of that has its own internally generated magnetic field, its own intrinsic magnetic field. So you can think of Ganymede as sort of having like a bar magnet in the middle of it, with these dipole magnetic field lines coming out from the center and surrounding the body, just like the Earth has and just like a bar magnet does. So you can think of scattering iron filings around Ganymede, and you might end up with a similar sort of picture. One of the really interesting things about this, about the fact that Ganymede has this magnetic field, is that Ganymede's embedded inside Jupiter's magnetic field. And as you might know, Jupiter's planetary system, its magnetosphere, its sphere of magnetic influence, is one of the most radiation rich, most hazardous radiation environments in the solar system. And this radiation is able to rain down, pour down onto the surfaces of these satellites. So if we look at Ganymede, we can sort of see different colors. So we can see a sort of a more bluish color up here, and we can see a darker, more muddy color in the equatorial regions, near equatorial regions. You can see it a little bit more clearly if we look at this grayscale image at the bottom left, which basically shows us a map of Ganymede in a cylindrical projection. So you can see that these equatorial regions are darker than the polar regions. And this is a consequence of this radiation that sits in Jupiter's magnetosphere, and also the fact that Ganymede has this magnetic field, because the regions where the magnetic field of Ganymede is able to extend out into space and connecting with Jupiter's magnetic field, these polar regions here are able to receive lots of this radiation from Jupiter's magnetosphere. It's freely able to stream down those magnetic field lines onto the surface, raining down into these polar regions. And when that radiation hits the ice, it alters the ice, making it brighter. But the near equatorial regions, they are protected by these magnetic field lines. That radiation can't get down to the surface. So we have this dichotomy between the polar regions and the equatorial regions. And this, the red, green, and blue lines on the bottom left figure, they show you that boundary between those magnetic field lines that are able to connect in with Jupiter's, and where that radiation is now freely able to get onto the surface, and the regions which are protected by Ganymede's magnetic field. So there's an interesting interaction there between this magnetic field that we can't see and effects actually on the ice, this weathering, space weathering of the ice. Going to a different planet for a second, I just want to take us to Triton, which is one of the natural satellites at Neptune, basically one of the thing that dominates the Neptunian system in terms of its natural satellites. And Triton is thought to be a Kuiper Belt object, as an object similar to Pluto and Charon, and was captured by Neptune. And one of the parts of the evidence we've got that Triton was captured is that Triton is in a retrograde orbit around Neptune. It goes around Neptune the wrong way, and it's also in an inclined orbit around Neptune. All evidence that this is a captured body. So we think it was originally in orbit around the Sun, but then was captured by Neptune. And that action of Triton being captured severely disrupted Neptune's original system of natural satellites. And what we see today, which is basically Triton and a few bits of rubble, and those bits of rubble basically all that's left over from this violent capture event. One of the exciting things that we saw on the surface is in the form of these splodges at the bottom of this image here. So we can see these sort of dark linear features at the bottom of the image here, these streaks. And it's a sort of thing where once you've seen one of them, you can't not see them. And the interpretation of that is that we are seeing geysers. We are seeing material that is underneath the icy crust, maybe not very far underneath the icy crust, and it's able to vent out up into space. So it's released into space. And the dark color there is thought to be because there's organic material, organic chemicals entrapped with that material. So it emerges as a plume, as a jet, as a geyser up into space. And then the very, very weak, tenuous wind on Triton, because Triton has the very tenuous atmosphere with wind systems, that wind system just gently pushes that material that's vented up into space, and then pushes it. And then it can rain down in this linear feature, just like filling up a fairy liquid bottle with some water and squeezing it up in the air when there's a strong wind. That material will all be pushed downwind from you to fall back onto the ground. And that's exactly what we think is happening here. So we've seen this from Voyager. We're seeing the planetary bodies can have material which can eject into space of its own accord, if you like. So let's go back to Europa. Why did I want to leave Europa now? So looking at Io and Ganymede, there we've got two very different bodies, not just in size, but also in what they look like. Ganymede is icy, it has this magnetic field that's produced in the interior. We have Io, which is a volcanic body. And when we look at Europa, we see something different to either of those. Europa could be thought of as a big ball of ice, and I remember science shows when I was a kid talking about Europa as just a big frozen ball of ice. But when we look at Europa, we see lots of really interesting features, geological features on the surface. We see these lines crisscrossing the surface all over the place. They have a slightly different color, and that's one of the things that people are very interested in, is what's going on there. One of the things that was discovered, and many things that was discovered by the Galileo mission in the 1990s when it flew past Europa, is that it saw a particular signature in the magnetic field as it flew past. So Galileo, as did Voyager, as did a number of other missions, they carry magnetometers. These are instruments that measure the strength of a magnetic field. They're a little bit like a compass, if you like. They can measure the direction that a magnetic field is pointing in, and also how strong it is. When it flew past Europa, it saw something we weren't expecting. And when we analyzed those data, when we looked and tried to understand what that signature was telling us, it had a very particular form, and that form was of a dipole, a magnetic dipole, a bar magnet, just like we see in the planets, just like we see in Ganymede. But that bar magnet was in a very particular orientation, and it was opposite to the magnetic field that it was exposed to from Jupiter. And that's a signature of what we call electromagnetic induction. What we're seeing is that there are electrical currents flowing inside Europa, and they're flowing inside Europa because Jupiter's because Europa is surrounded by Jupiter's magnetic field. And because Jupiter's magnetic field changes and flops around over Europa every time Jupiter rotates every 10 hours, that gives you a time-varying changing magnetic field at Europa. And one of the laws of physics that was discovered by Michael Faraday is that if you have that situation, then electrical currents will be produced to try and stop that change penetrating an electrical conductor. So it tells us that there is some region inside Europa which is in a liquid form so that electrical currents can flow in it. And it also tells us that that medium must be electrically conducting, because if it wasn't electrically conducting, we wouldn't be able to generate electrical currents, and we wouldn't be able to generate this magnetic field that we see. So that was one of the first pieces of evidence that within the crust of Europa, underneath this ice shell here, indicated in white, beneath this ice shell, there is a subsurface global ocean of salt water. Salt water because salt water is electrically conducting. And so it's in this layer that these currents can flow to produce this particular magnetic signature. And this is the focus of a lot of intense study now, especially since we have new missions going back to the Jovian system. For example, we have ESA's JUICE mission going to Jupiter, and a NASA mission called Europa Clipper. But this is not the only place where we think we've seen this. We think we've seen evidence for this at Ganymede, at Callisto, and also there's suggestion that it may also be present at some of the moons further out in the solar system. For example, Triton and this tiny moon at relatively small moon at Uranus called Titania. So, so that's sort of a whistle-stop tour of some of the variety that we see amongst these satellites in the outer solar system. So let's go back now to Enceladus. So what's the story there? And this really started with the Voyager mission. I mentioned that the co-location of the E-ring and Enceladus was a sign that there was something quite exciting going on there. But it took the Cassini mission for us to really figure out more of the details of what was happening. So this is a picture of the Cassini spacecraft. It's an artist's impression from when Cassini was going into orbit around Saturn in 2004. The spacecraft was launched in 1997 and had a sort of long trek through the solar system, flying past Venus, flying past the Earth, flying past Jupiter, all getting gravity assists to reduce the amount of fuel it would consume in trying to get us out to Saturn in good time. But once the spacecraft is out at Saturn, it's going quite fast, and so obviously you need to slow down in order to be captured into orbit around Saturn. Otherwise, they would just fly off into continuous journey through the solar system. So we find these main engines at the back to slow Cassini down so it can be captured into orbit around Saturn. And that happened on the 1st of July in 2004. I mentioned some of the different instruments that are on Cassini, and I mentioned some of the types of instrumentation that are used in some of these planetary missions, and I mentioned magnetometers, these devices for measuring magnetic fields. And Cassini's magnetometers are on this boom. So this boom here, this is 10 meters long, and the magnetometers are located here and here. And they're located far away from the spacecraft for two reasons. One, the spacecraft itself, there are permanent magnets on there. And so if you are flying past a planet, you want to measure the magnetic field of the planet or of the moon or of some other phenomenon, not the magnetic field of the spacecraft itself. So that's one reason. And the other reason is that these spacecraft are electrically powered. There are electrical systems on board, and electrical currents generate their own magnetic fields as well. And so we want to minimize the interference that we get from our carrier, from our spacecraft. We want to be able to remove that or minimize that in our measurements. So these are the magnetometers on this 10-meter long boom. These wire antennas that you can see here, those are electric field antennas for measuring radio emissions around Saturn. This sort of conical shaped structure down here, this is the Huygens probe. This is the European Space Agency probe that landed on Titan, on this largest moon of Saturn in 2005. And this white dish here, this is the high gain antenna. This is like like a satellite dish. It's the antenna that we use to do most of the communications between the spacecraft and Earth, and that's 4 meters across. So if we're using old money, that's what's something like 4 meters. So that's something like 12 foot, 14 foot maybe across. And this whole bus here is about the size of a minibus. The whole spacecraft here is about the size of a minibus. So it's one of the largest and most complex interplanetary spacecraft we've launched. And the rest of the surface here, you can see this covered with different instruments. and these are the power sources here for the spacecraft. If we were to look at this without an artist's impression, then these are photographs of Cassini. We have a photograph here on the left of the spacecraft partway through construction, and on the right here you can see the spacecraft with an engineer for size here. So this is Cassini in a vacuum testing facility, and you can see the size of Cassini compared to the size of these engineers, and these are regular sized engineers. One of the differences that you can see between these two photographs is that there's lots of this gold covering in the image on the right, and not really any on this side. And that's because the goal here is insulation. It's to be able to control the temperature of the spacecraft. So if we think about Cassini's journey out to Saturn from the Earth, it started its journey actually by spiraling towards the sun, and that was to take it on a flyby of Venus. So it had to get actually relatively close to the sun before going all the way out to Saturn. And so Venus is about 70% of the distance from the Earth to the sun, and the intensity of sunlight varies with the square of the distance. So that small change in distance in Earth and Venus is actually quite a big difference in terms of how bright the sun is. And then when you go out to Saturn at 9.5 AU, that's around about 100 times the insolation that you would get, the sunlight that you would get near the Earth. So I like to think of this as the engineering challenge of having of trying to stay warm but not too warm, and also keep yourself cool but not too cool, if you're walking between the North Pole and the equator and you could only wear one coat. And that's the challenge. That's what this insulation is really good at. It keeps the spacecraft cool when it's close to the sun, and it keeps it warm when it's far away. You can also see some of these red panels here. And these red panels, they also removed before flight. And they are covering particularly delicate parts of the spacecraft. And the idea is someone comes along before launch and pulls them all off. And then the spacecraft is launched. And that's because lots of these detectors can be corroded by oxygen, like the oxygen in our atmosphere. And so what they do is they flood the internal spaces with nitrogen in an inert gas, put these stickers on, and then just before launch, they pull them off, it launches into space, and the nitrogen gas naturally leaves the internal spaces as the spacecraft goes up into orbit, so protecting those delicate instruments. And one of the things that you can't see on this picture, but you could see on the artist's impression, if I just skip back, you can see these devices here. This is the power source for the spacecraft, and these are known as radioisotope thermoelectric generators, or RTGs for short. And this is an actual photograph of one of the Cassini RTGs. And this engineer is checking the radiation around this RTG. And here you can see the engineers preparing to attach one of these to the spacecraft. These are filled with cubes, packaged cubes of plutonium dioxide. And you can see the plutonium dioxide in the top left photograph. And there, this piece of plutonium is red, not because we painted it red, it's red because it's red hot. And so what's happening there is that you've got this pellet of plutonium dioxide, and it's a radioactive material, so that radiation there's particles of plutonium are decaying all the time. And every time one of those plutonium isotopes decays, it releases energy. It releases energy in the form of heat, which heats up this piece of plutonium. And so what we do is we stack these inside this RTG, and then we use the fact that this is really, really hot and space is really, really cold as a temperature difference. And from that temperature difference, we can generate electrical voltage, and we can then generate the electrical power that runs the spacecraft. And Cassini has 4 of these installed on it, 3 of these installed on it to provide the electrical power for the spacecraft. Okay, so that's a whistle-stop tour of this mission that arrived at Saturn in 2004. So let's take a closer look. Let's now start to drill down now on Enceladus itself. So these are just some of the basic facts of this satellite. It's not very massive, certainly not very massive in terms of the mass of the moon. I know 10 to the 20 kilograms is a very large mass, but a thousandth of the mass of our moon is relatively low. Its radius, though, is only sort of 15% of the radius of our moon. Radius is about 252 kilometers. I'm going to show you that shortly. Compared with the Earth, so with the UK, for example. So here you can see the UK is really not that much larger than the diameter of this picture of Enceladus. So we are dealing with actually a relatively small solar system body, certainly compared to something like Ganymede, which is quite large. Now we can measure the mass because we can fly a spacecraft past it, and so we can look at how a spacecraft moves in the vicinity of Enceladus and then get a measure of its mass. We can take a measurement of the radius, so we can look at a picture like this. We can look at it with a telescope and measure the radius of Enceladus. So two quite basic measurements that we can make. And then we've got the radius. So from the radius, we can find out the volume. We know what the mass is. And so from those two things, we can work out what the average density is. And we found out that the average density is 1,600 kilograms per cubic meter. So if we compare that with things that we know, I mean, so water has a density of about 1,000 kilograms per cubic meter. So it's not too far away from water or ice. And you might be forgiven for looking at Enceladus and saying, well, that's obvious. It looks like it's made of ice. But this doesn't, we're just seeing the outer crust there. We're not seeing very far inside at all. So this could be just a veneer of ice over the top of a big ball of nickel iron. And this measurement of the density shows that's not the case. It tells us that there's other stuff mixed in there, but it does tell us that a lot of that must be water or ice in some combination. It orbits around Saturn once every 1.37 days, and it's in a synchronous orbit, so it always keeps the same face pointing towards Saturn, or at least nearly always the same face pointing towards Saturn. So we've got this sort of basic idea. We've got this sense of Enceladus being largely water or ice with some other heavier, more dense material mixed in. And then we're in the Saturn system with the Cassini spacecraft, and we started to see quite interesting things. So this is an image of Enceladus. We're actually sort of looking at the South Pole. We're looking at Enceladus side on here, and the South Pole is over here. We see lots of interesting structure all over the surface. We've seen these linear features everywhere. We see things that you could almost be forgiven for thinking, oh, it looks like a river or something. We see craters here. Some parts of this terrain are quite cratered, some parts aren't quite cratered. One of the ideas we have from looking at Europa in the Jupiter system is Europa, we hardly see any craters at all on Europa. And so Europa has what we call a young surface, a fresh surface. There's a continual resurfacing process that's going on to remove those craters. So a crater appears, yes, we can't stop a meteor coming in and hitting the surface, creating an impact crater, but then relatively rapidly the surface erodes that feature and gets rid of it. And so we can see a similar thing going on here at Enceladus. We don't see very many bits of cratered terrain. But we do see lots of these linear features. And we think of these features as cryovolcanic features. These are pseudo-volcanic in that they're driven by pressure underneath the surface. We can force material up onto the surface, which can flow out onto the surface. There can be almost like tectonic plates just made with ice rather than rock. So we can have an analog of volcanic activity just driven with icy materials rather than rocky materials. So it's immediately telling us that this is quite an interesting body. There's lots of features on the surface, lots of geological features on the surface that tells us that it's very interesting. But then we started to see these jets. And these are the jets that we see coming out of the South Pole of Enceladus. So we see them coming out from these stripes, these cracks in the South Pole. We call these cracks the tiger stripes. So it looks like a tiger's coming with its claws and scratched at the South Pole. Now, the fact that these jets existed at all wasn't, or the fact that there was something interesting in the space above the South Pole of Enceladus wasn't discovered in Cassini images. And this is part of the story that I want to tell you today. This, the first hint that the South Pole was interesting, or the region above the South Pole was interesting, was discovered actually in this magnetic field magnetometer that I mentioned earlier. And so what was actually seen was a deflection of the magnetic field near the South Pole of Enceladus. So this artist's impression here, this shows you these bar magnet dipole magnetic field lines around Saturn, and they are dragged with gas, with charged particles that move around Saturn, that get dragged around Saturn by Saturn itself. And when these magnetic field lines encounter a natural satellite, you do expect some deviation, you do expect some interaction. You might expect these magnetic field lines to sort of slowly diffuse through the body itself. But in this case, we found that there was something happening towards the South Pole. This interaction was asymmetrical. One of the things that governs how these magnetic field lines are able to pass a natural satellite is how conducting the interior is. Is the interior a good electrical conductor? And in this case, we see this quite significant bending of the magnetic field line around the South Pole, around where these jets are located. And so what that tells us, what that told us in these data, was that the magnetic field of Saturn was getting hung up on something. You can sometimes visualize this as we take some magnetic field lines that you might think of as being honey or golden syrup or something quite viscous, and then we try and take some string and pull it through the honey, and the honey will provide some resistance, and so the string, the magnetic field lines, get hung up on this obstacle. So it tells us that there's an obstacle at the South Pole of Enceladus. What that is, we weren't sure. We do see similar things at other solar system bodies, but usually we see those if there's an atmosphere. So is there an atmosphere all the way around? If there is, and that atmosphere then could be electrically conducting through sunlight hitting it, but then you would expect something that was more or less symmetrical around the body. But in this case, it was very, very clearly confined to the South Pole. So that tells us that the South Pole is an interesting place. We have some of the geological information, and now we have this piece of evidence that something extending quite far below the South Pole. Remember, this is only 500 kilometers across. So there's something extending hundreds of kilometers above or below, depending on your perspective, the South Pole of Enceladus. So this tells us, gives us some invisible evidence, if you like, that something is happening. So we started to turn cameras on this, and this is an image from the side on, and it's in false color. And what you're seeing here, this band that you're seeing at the top there, this is the E-ring itself. This is Saturn's E-ring. We have Enceladus here, roughly in the center of the frame, and then at the bottom you see this asymmetrical plume coming out of the South Pole. So we're starting to build up this evidence that the South Pole is a very interesting place. We have this magnetic field evidence that shows us that there is some sort of extended cloud of material. Didn't know yet it was a plume, but some sort of extended cloud of material at the South Pole. We've got this geological evidence at the South Pole, and now we're seeing an image of material extending below the South Pole, starting to give us this picture of a plume at the south of Enceladus. We start to zoom in, we start to do closer and closer flybys of the South Pole and start to see these cracks, these fractures in a lot more detail. We start to see higher and higher resolutions. We start to be able to resolve more and more detailed features. One of the intriguing pieces of evidence was when we pointed one of the Cassini's infrared cameras at the South Pole. And this is what was measured by this instrument called SEERS. This is the Composite Infrared Spectrometer. And SEERS can tell us regions that are warm and regions that are cool. So this is the grayscale background here is a picture, a visible picture of the South Pole in the center here. The tiger stripes are denoted here in these features. And the tiger stripes are known as Alexandria, Cairo, Baghdad, and Damascus. And the color overlay is an image from SEERS. And the color scale there shows you regions that are cool in the purple colors and regions that are hot in the reddy, orangey, yellow colors. And so we immediately see from that that the tiger stripes are hot compared to their surroundings. They're warm compared to their surroundings. And when we zoom in a little bit more, down to scales of tens of kilometers, we start to see very, very concentrated regions that are warm along the tiger stripes. So again, this geological evidence that something interesting happening there. So what's actually happening? So we can see these pictures side on. We started to take images from the side on perspective, starting with the first picture that I showed you from quite far, where we could see the larger scale plume coming out of the South Pole. But then as we started to get closer and take pictures side on, we started to see that the plume was a large structure, but within it was the additional fine structure. We could start to see individual jets, not just off the limb here. This is the same picture that I showed you on my introductory slide, but also you can start to see these things coming out from discrete locations on the South Pole. And again, like I said, we started to look at these features in even more detail. So we're starting to look here down at kilometer scales, half kilometer scales, and starting to see very, very fine detail. So we found all these jets, and these jets are were seen in imaging studies. But of course, this is just a two-dimensional view. And so what the team were able to do was they were able to photograph Enceladus from one direction and track out where we saw these plumes, and then look in another direction and see and track where they found these individual jets. And from those different stereoscopic images from different viewing vantage points, they were able to then say, this is the location on the surface where they're coming from. And you can almost see that, get a sense from that in this image, showing sort of a linear origin on the surface. But then when they actually mapped out where all of these jet sources were, they found that they lined up very, very nicely with the four tiger stripes: Alexandria, Cairo, Baghdad, and Damascus, again centered on the South Pole of Enceladus. So this is building this picture of tiger stripes being interesting. Now we've got that material coming out of the South Pole. You can see it in the images. We can see this material here. We can see it scattering the light. But what is it actually made of? You might say, well, it's water then, right? It's the thing is 1,600 kilograms per cubic meter average density. It's going to be water, and that's I don't think I would necessarily disagree with you. But we can actually do a good job with Cassini, where we can fly through the plume and we can actually sample that material, because Cassini carried the instrumentation to be able to do that. And so in quite daring maneuvers, we flew the spacecraft relatively at relatively low altitudes over the South Pole and pointed our instruments into those jets so we could collect the particles of material coming from inside Enceladus, take them inside the spacecraft, examine their composition, find out what they were made of. And so to answer that question, is it just water? And this is one of the one of the measurements that was made. This was made by the ion and neutral mass spectrometer instrument on Cassini. That's what INMs stands for. And the details of this figure are not especially important, but the coloured bars indicate different molecules, different chemicals. Roughly speaking, as we go from left to right, we see heavier species that are heavier and heavier, so that they've got more atoms wrapped up in those molecules. But we, as you might expect, excuse me, we see quite strong peaks from water, H2O. We see these peaks. So if you want to get into the details a little bit, H2O, a hydrogen atom, we could say weighs 1, an oxygen atom weighs 16. So H2O in these units weighs 18. And so we see the peak at roughly 18 on this graph. So this is water, as expected, but then we see a whole other zoo of additional chemicals. So we see a signal from methane, CH4. We see signals from ammonia. We see signals from carbon dioxide, argon, and then all of these heavier carbon-bearing organic molecules. And of course, carbon-bearing organic molecules are the sort of the stuff of life, if you like. And so this gets people very excited about what's actually happening inside Enceladus. What are the processes that are going on to produce these quite complicated molecules, these quite complicated heavy molecules? There must be a process that's driving that. And is that an actual biological process that's producing that? Or could it give rise to a biological process? But we can also look at other components of those jets. So this is looking at the gas, the vapor that's coming out. There's also solid material that comes out. And Cassini carried a dust analyzer called the Cosmic Dust Analyzer. And that was able to look at the tiny particles, the very fine material that was coming out along with the vapor. And so when we talk about cosmic dust, we're really talking about very, very, very fine particles. So not the sort of dust that you would get out of your carpets with your vacuum cleaner. We're talking about material that has sort of like the texture and size of cigarette ash. Really small stuff. But one of the things that we were looking for was the presence of salts. Because salts tell us a lot about what's happening underneath the surface. If we're seeing salts mixed in with water, that tells us that water is in contact with rock, so that these salts can leach out of the rock to make it salty, reach out of the rock to make the water salty. And so the signal from the Cosmic Dust Analyzer was able to see large peaks in its spectrum. This is a similar sort of graph to the one I showed you on the previous slide, looking at those molecules, but here we're looking at dust grains. And so here we wanted to see signatures of for example, sodium chloride, common table salt, NaCl, caustic soda, NaOH, sodium carbonate, washing soda. So these are the sort of things you might have in your kitchen. And we're seeing them, the Cosmic Dust Analyzer saw them in those jets coming out from the South Pole of Enceladus. So a very, very exciting observation that tells us that there is the water that's forming a lot of that plume, a lot of the jets, has at some point been in contact with rock. So that has implications then for what's happening underneath the surface. So we started to construct these pictures of what's actually happening underneath the surface. So obviously there must be a source of liquid water underneath that icy surface, and somehow that water is making its way through that icy crust to the surface to be vented out into space to form these jets. So one of the ideas that was distributed and shared and discussed at the time was that, okay, so we've got a rocky interior, we have got a layer of liquid water, a little bit like the layer of liquid water in the subsurface ocean at Europa. And then overlying that, there is an icy crust. And at some locations, we have these vents that take us out to space, leading up to the tiger stripes, where these jets can then form. And so we have this water that's in contact with the rock. The salts leach out into the water along with other chemicals. And then that is materials under pressure, and eventually this vents out into space, carrying those salty compounds with it. And we started to continue to develop that picture and add additional texture to it. You know, so we could have a whole network of cracks and caverns and roots that go from the subsurface ocean, or at this point we were thinking that it was a subsurface, more like a subsurface lake, like a confined region of liquid water under the ice, not a global ocean. We can have that rocky core doesn't need to be a solid rock boundary. It can be porous, so water can get in there. And then we can have some actual volcanic, some geological processes on the ocean floor, and this rocky ocean floor, where we can have some interaction, where we can start to feed hot water via hydrothermal vents into the ocean to make that ocean warm and to enrich it chemically. So we are building this picture up with observations from Cassini, and we're starting to get really quite detailed information or detailed insights into what's happening down in this ocean. So I just wanted to talk about a little bit about how we actually made some of those observations. And so I've got a movie to share, and I'll post the link to this movie into the YouTube chat on the night. But I wanted to show you the sort of the complex dance that Cassini was making in order to capture these, in order to capture the data that we based a lot of these ideas on. And so what we're going to be looking at here is this is a simulated synthetic view. We're riding along with the Cassini spacecraft on the left, and what we're going to be doing is we're going to see Cassini turning around all the time to point different instruments at the spacecraft. So you can imagine this is a little bit like saying I've got two cameras and they're pointing in different directions in my hand. And if I want to take a picture with this camera, I'm going to turn my whole self to point it at the thing I want to take a picture of. But then if I decide I want to use the camera in the other hand, I've got to turn my whole self around in order to make that, because these cameras are all pointing in slightly different directions. So that's what we're going to see on the left-hand side. And then on the right, we're going to see what exactly Cassini is looking at that time, when we're going to see the field of view of that particular camera or detector as this goes on. So I'm going to start this video now. So you can see there that this is the field of view. Cassini is looking at Enceladus there. You can see this camera called VIMS. This is an infrared instrument looking near Enceladus. And in a second, you'll see it's swept out now. We're now looking at Enceladus with a narrow angle camera. Now the spacecraft sweeping across Enceladus with its high gain antenna, almost using it as a radar. So here taking many mosaics to try and get really high resolution views of the South Pole. And now it's at this time when INMs and other instruments are turning on and being able to sample material in the plume. Here we're scanning across the tiger stripes, looking at the temperature. And then finally, it's after we've taken more measurements at different distances away, so we get different viewpoints, different perspectives. Then once all of this information has been collected and stored on board the spacecraft, it turns around, it points its high gain antenna at the Earth and transmits all of those measurements back to Earth in what we call a downlink. So all of those maneuvers are all pre-programmed and uploaded to the spacecraft from engineers on the ground to tell the spacecraft what to do. And that was done for all of these different Enceladus flybys in order to collect the information and build this picture up that I'm presenting you today. So we've got lots of these, we collected lots of these data sets from these flybys, and we started to see that some of these jets went out in really odd directions. And because we've got lots and lots of these images of the South Pole of Enceladus from lots and lots and lots of different perspectives over time, we can do a much better job of triangulating where the jets are coming from on the surface and what their orientation is. You know, are they pointing off at weird angles to the side? Are they going straight out or what? And indeed, are they turning on and off with time? And so this picture on the left here, all of these different colored stalks, like straws, these are all show you individual jets that were identified and triangulated in multiple images from Cassini. But it has been argued that actually are these individual jets actual individual jets, or is there some other explanation? So we started adding different layers of texture to this. And so one study that was done shortly after this was to pose the question, is there another explanation for this? Is there another explanation for the appearance of different brightness features that are interpreted as individual jets? Is there another way to interpret that data? And so what these authors did was to say, well, what if there are multiple curtains of material and it's all coming out in like a sheet? And like curtains in your living room, maybe even in your living room right now, those curtains can have some ripples to them. And so if we look at a curtain of material, you imagine like a waterfall, but in reverse, if that has some folds in it, there might be regions that look brighter than others. And that's what these authors have argued, that actually we're not seeing individual jets, we're actually seeing curtains of material that can be corrugated and warped, and that actually gives the false appearance of individual jets. But I don't think this story is entirely closed yet, and we've still got lots of Cassini data to look at. So we're still focused on these plumes, and I talked about maybe there's just a pocket of water underneath the icy crust. And that started to be relaxed a little bit more as time went on. And the geophysical evidence that we built up was actually, well, maybe it's not just a narrow pocket. Maybe actually this ocean covers a much wider range of latitudes under the ice at the South Pole. But it still could mean that the rest of this of the North Pole, where we don't see any of this activity, maybe this material was actually just liquid here, but solid everywhere else. But more and more observations have been analysed, and the conclusion is now actually that this ocean is global. And this is the picture that we have an ice shell in the light blue colour here, and the darker blue colour here is this global subsurface ocean underneath this icy crust. And so that evidence comes in two forms. One piece of evidence is that is from the gravitational field of Enceladus itself, and that's one of the windows that we have into the interior. And this is all about how does the spacecraft move as it flies past a body, and the internal distribution of mass that controls to a certain extent how this spacecraft will fly past a body, and that allows us to infer what the internal structure is. The other piece is to do with what face is pointing towards Saturn. I said that it was a synchronous rotator. It kept the same face pointing at Saturn. And that's true, except that if the ice shell, if the surface were decoupled from the interior, if there was a global ocean sitting between the surface ice and the rocky core, then there could be some differential motion between the two. So effectively, the icy surface could lag what the core was doing. And that's what a study had done, is that they actually tracked the motion of features on the surface and determined that actually the data best fitted the idea that the ice shell was floating on top of this subsurface ocean, and so it could move quite separately. So they were able to measure this, and this again was another part of the evidence of Europa as well. You might also be able to tell from this picture, from this schematic, this artist's impression that the ice shell is not a uniform thickness. I think that's one of the really cool and interesting things that's come out of this work is the idea that ice shell is not uniform in thickness. And we have this, we draw these artist's impressions, but I think it's very exciting to sort of shake that notion that things are not nice and symmetrical and uniform. And so there have been some studies that have looked at this and tried to infer what the thickness of that ice shell is from the data. So this is no longer an artist's impression, this is a calculated ice shell thickness. So the color scale here shows you the thickness of the ice. The bluer colors, so for example, over here and over here, that indicates a thicker ice shell. So here we're in the tens of kilometers, nearly 40 kilometers thick ice shell. And then the redder colors, and the yellows through to oranges and reds, they indicate a thinner ice shell. So down to only 4 kilometers thick at the most. So we're down to sort of 3 miles or less than 3 miles thick. And you can see that that is concentrated at the South Pole. There are some regions near the north that are a bit thinner, but by and large, the South Pole has quite a thin ice shell. So that's consistent with this artist's impression here of a thinner region here. And maybe that's why we have all of these jets coming out of the South Pole, is that is the thin part. That's where it's easier for that material to get from the ocean to the surface and then out into space. Now the question is, well, why might this South Pole be thinner? What's the reason for that? We still haven't explained the basic asymmetry between the North and the South. Why is it the South Pole that's exciting? And one of the ideas was that when Cassini arrived at Saturn, we just passed southern summer solstice. So we just passed the time of year when the southern hemisphere was illuminated most by the sun. Excuse me. So maybe it's sunlight. Maybe sunlight is heating the South Pole, and maybe that behavior will reverse when we go into northern hemisphere summer. That didn't happen. The South remained as it was. So one of the ideas that's been worked on recently with modeling is to look at what happens if that rocky core inside Enceladus, that ocean floor, what if that is not a perfectly smooth ball? What if that is asymmetrical? What if it has lumps and blobs and tiny mountain ranges, just like the Earth's ocean floor has? And people have modeled this, and they've looked to say, well, if we do make it asymmetrical, how does the heat flow come out from that ocean? How does it make the water move? So the idea being that if the core is some sort of strange, lumpy, potato-shaped object, then the heat that flows out from it will cause convection to go in weird patterns, maybe preferentially heating the South Pole, and so therefore melting some of the underneath of that ice shell, making it thinner at the South Pole. And so we have these sorts of ideas of these hydrothermal vents that we see in the Earth's oceans. This is a hydrothermal vent from the Earth's oceans. These what sometimes called black smokers, where we have volcanically heated water, superheated water that's been vented up into the ocean. It creates these features because of all the dissolved minerals in the water. They sort of leave these columns, and they become a rich environment for life. So you look at these and in the Earth's oceans, and you see them covered in sea life because it's a source of warmth and it's a source of chemical nutrients. And so that's one of the things that makes us very excited about Enceladus. What is going on in that core ocean interface? Is it just a relatively simple matter of a chemical exchange, or is there something more exciting happening? Is there such a thing as an Enceladus prawn living down there underneath the ice? So these plumes, we've seen them from afar. What are the wider consequences? And I said at the beginning that the E-ring was best seen when the E-ring was between you and the sun. And this is a relatively famous picture of Saturn with the sun on the other side. So we have Saturn in the center here, we have the rings, and we have the sun on the other side. And so what we're seeing the rings here in forward scattered light. So the sunlight is shining through the rings, and is being scattered by all the particles in the ring to come forward towards you, a little bit like seeing steam through sunlight. So we're seeing it much more brightly. And this really does show up the E-ring very, very brightly. And you don't see this as brightly when we're looking at it from the Earth, because you're seeing it in backscattered light. And the sort of water vapor and dust in the E-ring does not backscatter light as effectively as it does in forward scattering. And we can see again this picture of Enceladus being at the core of the E-ring. This image is a composite of multiple pictures stacked on top of each other. And in this picture, you can actually see Enceladus 3 times. So there's Enceladus over here, Enceladus is here, and Enceladus is here. Again, showing this idea from Voyager that Enceladus is the heart of the E-ring. And this material that you're seeing in the E-ring is the product of all of that material in the plume. And in fact, when we zoom in on these sorts of images, we can really see the plume and how that plume is actually interacting with the rest of the bright part of the E-ring. And indeed, we can start to see Enceladus casting shadows onto the E-ring there. And so the last thing I wanted to close with is just to continue with this idea of the invisible. And that's that this is an artist's impression showing Enceladus, showing the plume, Enceladus in orbit around Saturn, and showing these magnetic field lines. Here the magnetic field lines are in yellow, and this is a bundle of magnetic field lines that connects Saturn to Enceladus and back again. And when we look at similar things in the Jovian system, we see that these magnetic connections between the planet and the satellites give rise to spots. So this bright spot here with this tail, this is Io. This is where Jupiter's magnetic field connects Io, that volcanic moon deep within the Jovian system. That's where that magnetic connection is rooted in the planet. And it produces a bright spot in the aurora. This is in the ultraviolet. We see other spots associated with the other satellites. So the next one in is Europa, and then we have Ganymede. We would expect something similar at Saturn. We would expect that at the foot of this magnetic field line, where it connects to the planet, we would expect to see an auroral spot. And this was searched for a number of times over the years. And it remained elusive for some time until it was finally detected. And so these are ultraviolet images of Saturn's aurora. You can see Saturn's main aurora here forming this sort of approximate ring around the pole. And then you can see this spot here. And it was shown that this spot was actually mapping to Enceladus itself, although this spot was a lot weaker than the equivalent spot on Jupiter. So with that mystery solved, I'm going to leave it there, and thank you very much for watching. Yeah, and I'll happily answer questions on the YouTube chat.
Well, thank you very much indeed, Chris. Excellent talk. I think that just really confirms what an amazing space probe the Cassini-Huygens mission was, with some of those stunning images and great science that's come out of it. So we'll just get on with the live chat. So if you've got any questions for Chris, please submit those now on the YouTube live chat. And Chris has joined us live now to take questions. I'll probably kick off with one for me, if that's okay, Chris. I don't know if you want to just turn your video on. We've said that liquid water's there behind the ice sheet. Certainly originally they weren't sure whether there was enough heating from tidal effects to sort of create that amount of liquid water. What are the latest thoughts on that?
So that's a really good question, and actually I've been doing some work recently on some of the icy satellites at Uranus, and looking at if they may harbour subsurface oceans and whether they might be detectable from a future mission. And the models that I've been studying recently, they predict no ocean at Enceladus. So it's a really good question. Those models don't include the tidal heating, but even even back in the day, people were saying, well, tidal heating is not enough. Some of the more recent work, I mean, in the last couple of years, has looked at the tidal heating in the cracks, and actually the fact that there's topography and that there is actual structure on the surface, that it's not just a monolithic ice sheet, seems to suggest that locally enhances the tidal heating rate. So I think it's generally what I'm reading more recently is that no one can think of another source of tidal heating. But the question is, how do you get the magnitude?
Okay, Chris, we're just struggling a little bit with your audio and video. I'm not quite sure if there's a problem with your connection at the moment. Might be worth if you could just try and turn your video off to see whether that helps with the bandwidth. Okay, I think Chris is actually just going to try and reconnect because he's just dropped off the meeting. So we'll just give him a couple of seconds just to get back on the connection. Whilst we just wait for Chris to return, then I'll just have a quick go over our upcoming meeting program. So our next meeting after tonight will be on the legacy of the Hubble Space Telescope, which will be by Dr. Steve Barrett. That's on the 1st of October. And our meeting on the Plum Tree on the 17th of September. Hopefully we're going to do some planetary imaging. So fingers crossed that we can do that with some clear skies between now and then, and we'll hopefully do that for the Plum Tree meeting in a fortnight's time. Right, Chris hopefully is back. Sorry, Chris, you dropped out there.
Yeah.
So, that sounds a lot better. So I was just telling members what we've got coming up in the next couple of meetings. So we kind of had most of you answer that question. So
yeah, it's about how do we get that tidal heating? We think that's the mechanism, but the question is, how do you get the amount that you need? And so attention now is starting to focus on the structure of the structure of the ice sheet, and the fact that because there is topography there are those cracks there, that might be a focal place for the tidal heating. It might almost enhance it locally.
Okay, great. Well, that's good because we've had time for the questions to come in. So we'll ask some members' questions. You should be able to see the question on the screen. I can quickly read through them. So one from Julian: do we think that the ice shells rotate at the same rate as the rocky planet?
So that's a good one. I think we know we've got the tidal forces that force the satellite to orbit Saturn and keep it in a synchronous rotation. Those tidal forces will apply to that rocky interior and the rocky planet part in the question, and also to the ice shell. But they're at different distances from the center. They're at different sizes, so the forces will be applied in slightly different ways. So I think overall, yes, they'll be rotating at roughly the same rate. But what I expect is that there to be regular wobbles in that rotation rate, both because of the shape, just the shape of Enceladus's orbit. It's very, very slightly elliptical, and also the motions of the other satellites around it. So they will apply different tidal forces to the shell and the core at different points in all of their sort of mutual dances around Saturn.
Cool. Another question coming from James: has the idea of a potato-shaped core been postulated for other worlds prior to Enceladus?
I would be surprised if if until now everyone thought, well, that the core of Europa and Ganymede and so on is just this perfect sphere, I would be surprised at that. I would be surprised if people weren't thinking about some sort of odd potato shaped or, you know, unevenly shaped core. But this is the first time that I'm aware that people have said, well, okay, let's start with a position that it is lumpy and bumpy, and let's see what the consequences are. That's my take on that.
Okay, a question from our chairman, John Hurst. Do the samples gathered from the jets indicate the possibility of primitive life?
Not to my knowledge as yet. My view on this is that extraordinary claims require extraordinary levels of evidence, and so it's a little bit like the history of the search for life on Mars has been littered with potential biological interpretations for a particular observation. So, like the Allen Hills meteorite, if anyone remembers the Martian worm. That was back in the 90s, you know, and subsequently we found, oh, there are non-biological explanations for the features that were seen on that meteorite. Some of the measurements from the Viking land or on Mars, they were taking samples inside the instruments and doing analyses, and there were some hints there that there might be a biological interpretation for the signals, but you know, it's always very, very tenuous. There's always another explanation, and that's the case with the Enceladus observations. So those samples from the jets, you know, yes, you could say, oh well, the carbon and the organic molecules, the carbon-bearing molecules, yes, they might have a biological interpretation, but not yet. But we don't know for sure because there are other interpretations that are inorganic. One of the things I did read recently is someone talking about what happens if there are very, very simple bacteria that are in the water and then get wrapped up in the material that's vented out in the plume, or maybe they get frozen onto some of these grains that then are ejected. But the results seem to suggest that at the altitudes Cassini flew past, we wouldn't have seen any of that material because it was sufficiently heavy that it would rain out already, and that you would have to get down to, I believe it was a flyby measured in sort of kilometers over the surface for you to actually be able to fly through that material. So it's almost like the material differentiates itself in what falls down first, and the more organic stuff might rain out first. So no, I don't think the samples gathered from the jets do indicate the possibility of primitive life, but they're enough of a hint that the interior is at least partially conducive to it that make us want to go and probe this question deep in more depth.
I read somewhere that the instruments work by having scattered starlight reflecting off the particle in the plumes. Is that how they work?
Some of those observations, that's how some of the observations are made. So on the clip you saw, the little movie clip, when you were looking at Enceladus with one of the ultraviolet cameras from Cassini, and you could track a star that was moving across the field of view, across the slit of the instrument, and that was the UV instrument there was monitoring the starlight as it went behind the plume, so you could see how that ultraviolet light was extinguished as it went through the plume. That has been used for sure to determine the composition of the material. The observations I focused on in the talk were they were basically mass spectrometers. So they were, as we flew through the plume gas is coming out at 500, 700 meters per second, and the spacecraft was flying past at about 14 kilometers a second. So this is like driving really fast into slowly drifting snow. that's the speed of that coming down is nothing compared to the speed that they're barreling through. So as we were flying through, we did basically pointed the aperture of the instrument into the oncoming jet, and we just collected those samples. They went inside the instrument. Because we're dealing with neutral molecules, so not charged molecules, they were then ionized within the instrument and then accelerated and then put through a mass spectrometer to figure out what their mass was. So that's another way to do that instrument. The dust is slightly different. The dust, that's measured in a more complicated way, but basically those dust particles, they come in and then they strike they strike a detector, a plate inside the detector, and the energy of the impact vaporizes the dust grain, and the resulting the vaporized dust grain is analyzed to see what material was in there and how massive it was and so on. So there's a whole range of different types of instrumentation to bring to bear that all tell you a different part of the story. And then the challenge then is to bring these different observations from different instruments that are maybe probing different parts of that plume. That's not just homogeneous gas, it's gas, molecules, dust. We've even seen snowflakes in there. So so a whole range, a whole zoo of different stuff, and we need to get that full census, really.
Tony asks a question about what temperature would the liquid water be with it being under pressure of the thick ice sheets and having dissolved salts within it?
Yeah, so I don't know the number, but yeah, absolutely, yeah, it does change the freezing point. So it does allow a wider range of temperatures where it can be liquid. The other thing that also changes the freezing point is the presence of other what we call in planetary science ices. So there I'm talking about things like ammonia and methane in addition to water. So I don't mean ice as a statement about the physical state of the material. It's just in a planetary science context, we talk about those three molecules being ices, but the presence of those can change the freezing point as well. So particularly ammonia, you add a little bit of ammonia in and it's like antifreeze, it changes the freezing point. And that's quite important. Some of these models in trying to figure out the tidal heating is that you don't quite know how much ammonia is in there at depth. And so, you change that fraction of ammonia and you can change the extent of that ocean quite considerably.
Okay, two probably questions to put together here. So one from Lee and also John. Are there any future missions to try and detect life, and could even a sample return mission be feasible?
So that's yeah, really good. So there are ideas on the table for return missions. I'm currently involved in a process that the European Space Agency is doing to figure out some of the next big missions that we'll be launching up to 2050. And some of the submissions we've had to that process have been missions to go back to Enceladus, go into orbit repeatedly, sample these plumes, do a much greater job, much deeper job of serving the geology, all of that volcanic activity, do a much better job of characterizing the gravitational field of Enceladus. So I mentioned in the talk about the gravitational field being able to distinguish these different layers inside, and with more orbits and over a longer time base, you can get a much higher fidelity picture of the interior, remote picture of the interior. So yes, the characterization of the plumes and the possible detection of life would definitely be a focus. One of the ideas that we're drifting to is questioning our definition of habitability. And this is a focus of ESA's JUICE mission going to Ganymede. So we've got this idea of Earth being in a Goldilocks zone away from the sun, where you go to Venus and it's a bit too close and a bit too hot. You go to Mars and it's a bit too far away and a bit too cold for life, and Earth is in a sweet spot. But we're seeing all of these really interesting environments out in the outer solar system, and it makes you think, well, okay, have we been thinking about this wrong? And actually, instead of looking for little green men on Mars, we should have been looking for dolphins on Europa. or fish in the seas of Enceladus and things like that. So yes, certainly trying to, if not to detect life, to continue the searches for those markers. And like I said earlier, I think it's extraordinary evidence. And so that, I think that's part of what motivates people to want to go through the ice and go into the subsurface ocean. And that people talk about this quite seriously for Europa as well. Of course, the challenge there is getting through 4 or 5 kilometers deep through the ice. And so people are actually doing experiments on this in Antarctica. They basically put some sort of submarine type probe on the ice, and it has a heat source, and it basically melts a hole all the way through into the subsurface. So people do genuinely talk about that, but the technical challenges are immense in that, it will refreeze above the probe. If you've got to get through 4 kilometers, that's 4 kilometers of cable. There's all of this cryotectonic activity going on that could easily sever a cable. So there are all sorts of really, really extreme but exciting technical challenges to doing that. Could a sample return mission be feasible? I think the challenge there is getting out of Saturn's gravity well once you're there. I talked about Cassini having to fire its engines to brake and go into orbit. You've sort of got to do the inverse of that to get out of that gravitational well once you're stuck there. And there's the additional problem of you probably would have to, if not go into orbit around Enceladus, get yourself into an orbit where you were going repeatedly through that plume. But we've had missions that have done something similar to that. There was, trying to think of the name of it, see, either Genesis or Stardust, maybe both. There was one that was collecting particles from the sun, and there was one that was collecting particles from a comet tail. I can't remember which one. And then they just had that descend to Earth. So that, in principle, that's possible. Certainly in principle, that's possible. The challenge with this, as with doing a sample return mission from a comet, is getting those samples back in a way where you're sure that they haven't been modified. So if you do collect molecules from those plumes and they do come back to Earth, and you find a broadly similar fingerprint to what we saw with the orbiter, how do you know that some quite big complex organic molecule, maybe sort of like a proto-RNA, proto-DNA type molecule, or an amino acid, how do you know that hasn't been broken up during the heat of re-entry, or has been broken up with radiation during the transfer from Saturn back to Earth? So that's always the challenge, is matching it back to what it could have been. So I think sample return is feasible, but the question is, what would you get from it? And can you bring back enough material to make it worthwhile? And again, this is the question we've got with comets. You can bring back a few grams of material, but people talk about, they want a meter-long ice core from a comet, or they want 10 kilograms of material. And that is pushing what we're able to do at the moment. Not necessarily technically, but more in terms of just the scale of that mission that you need to launch. It starts to become expensive quite quickly.
Are there actually any missions in the pipeline to go back to Saturn or Enceladus at the moment, or I've not heard of any?
So there's a mission called Dragonfly, which is going to Titan. And that is going to, it's exactly what it says on the tin. It's going to basically fly around. Just like a dragonfly. So that, to me, that's very exciting. That's very exciting. I think that is really breaking the mold of what we do on the surface of a planet.
Okay.
In a similar vein to me as the submarines. That's you get down into a liquid layer and you start looking at an ocean floor on a different world. I mean, to me, that's really something else.
Yeah. If we get a helicopter, then we perhaps might start to be able to bore down into the ice. Julian asks, would you like to see missions to Uranus and Neptune or back to Saturn if you could choose?
For me, I would say Uranus or Neptune. But that's my bias. For me, there is also the question of, do you drill down in one narrow area of focus, or do you say we want to collect information from all of these disparate bodies and try and collect all that information together? And so for me, I think, we've had a long time at Saturn. We've got a lot of data that's going to keep us busy for quite a long time. I started work on Cassini 17 years ago, and I've got PhD students that started with me a year ago that are working on the data, on some of the first data that came back 17 years ago. So it's for me, there's still lots and lots of data and still lots and lots of things we can find out about the Saturn system, but we've got such limited data from elsewhere in the solar system. And so to me, it's like we've got really quite a comprehensive understanding of Saturn and Jupiter. Let's look somewhere else where there are many mysteries to unpick. But that's my bias.
Would you look for geology or biology, or both?
As I've said, I think the problem with the biology is all of the things that it could be instead of, and so you'll find stuff out, but you could easily refute it. So it feels to me, in a rather blasé way, it feels to me that unless you're sat on Europa, shaking some European carp around on the end of your fishing rod, someone will always be able to say, but, and not necessarily in a mean way, but just in all of these different explanations. So there's such a high bar there for something that has a lot of, as well as it being very interesting scientifically, for a lot of people, it's got a lot of religious implications. And so for something that has such far-reaching consequences, I think that it's appropriate that the bar is high. Do I go there for geology? I think you get so much from the geology, and actually, I'm not a geologist. I'm one of the guys that studies the particles that are in space as we flew through the Plume. I'm not a surface geology person, although I find it absolutely fascinating. I do like. So I think I would focus. For me, it would be more on the geology side, but with the facility to collect those particles from the inside, because they give you geological cues. It's the finding of the salt in that plume that gives you geological information, but it also allows you to sort of prod away at those biological questions as well. So it's not necessarily on the fence, but it's just one of those things of, well, what can you find out the most? What are the most pressing questions, tempered against what can you answer? What can you say with the measurements that you get back?
Okay, I think we've got time for one more question. That one from Fred. Has the formation of the rings of Saturn changed the dynamics of the gravitational heating, and may have this been more significant in the past?
I would say indirectly, yes, because the rings are not static, and there's been some recent work that has talked about the evolution of the orbits of some of the inner satellites, including Enceladus, as an interaction between the rings and the satellites. So the rings and the satellites are in this gravitational interaction, this gravitational dance. A change in the structure of the rings, opening up gaps and things like that, they will change the orbits of those satellites. They will change the characteristics of the tidal heating. So yes, there is a co-evolution. There's certainly a co-evolution, so I like that. They're absolutely not independent at all. They are all coupled, and then the question is, how do you unwind all of that evolution over millions and millions of years? I said they're almost static, but we're talking over timescale, geological timescales. So you've got this interaction going on all the time. And just like with the Earth's oceans, some of that energy is dissipated as in friction. Some of the energy of the Earth-Moon interaction, some of that tidal energy is dissipated on the seafloor with friction between the ocean floor and the water that's been driven by tides. So that's really it then becomes a very difficult problem to unwind it back in time. Even though we can do an amazing job with some of these sort of, I would call it ring archaeology. If you've seen some of the work where people have seen some of the corrugations in the rings, and they wind that backwards and are able to say when that something impacted the rings, even down to the month of a particular year. We can do really interesting stuff like that. But trying to unpick all of the evolution over millions of years of all of these different bodies is quite a tricky thing, but very, very interesting.
Brilliant. Thank you very much for that. And someone just posted on the live chat, it's Rhiannon's last meeting with the Society before she goes off to university. And as coincidence would have it, she's off to Lancaster. So hopefully you'll be welcoming her very soon to Lancaster University. So
that's super. Yeah, come and say hi. Come and knock on my door if we're actually able to see each other in person. Come knock on my door and say hi.
Yeah, so best wishes from everyone at the Society to Rhiannon as she makes the move up to Lancaster. Thank you very much, Chris,
You're
for
welcome.
the talk and taking the live questions tonight. And I'm glad you managed to rejoin after the video difficulties. Otherwise, it would have been interesting me trying to answer questions. But yeah, we really appreciate your time preparing to talk the talk tonight and taking questions. So thank you very much.
There's one question I can just see there that I'm not sure I answered. That was the distance that the plumes extended to, and I can answer that super quick. And that's that you can see them on some of those images down to 1,000 kilometers, 1,500 kilometers below the South Pole. But in effect, because those plumes are starting to form the E-ring, actually you could consider it to be over a much greater distance. But it also does depend on what you're actually looking at. Are you looking at the ice? Heavier stuff might fall back down to the surface. Lighter stuff might go much further. Sorry, I don't want to leave that one unanswered.
Oh, thanks for spotting that. Brilliant. Thank you very much. And hopefully we'll see you again sometime back over at the Society.
I look forward to it. Cool. Maybe in person next time.
Yes. Thank you very much, Chris.
Okay. Take care. Thank you. Thanks for all the great questions.
Okay, so just a quick reminder, we mentioned it earlier, the meeting's coming up. So our next meeting on Thursday the 17th of September, again online. The meeting hopefully will be on planetary imaging and data processing, but we will confirm that in a week or so. And our main meeting for October, the 1st of October, is the legacy of the Hubble Space Telescope by Dr. Steve Barrett. Steve gave us a really excellent talk last year on the Hale telescope, so that'll be one not to be missed. Okay, thank you very much for joining tonight. We'll see you all in a fortnight's time. Have a very pleasant evening. Good night.